Welcome to This Explainer. Today we're going on a pretty fascinating conceptual factory tour, pulling back the curtain on the invisible magic of chemical plant systems operations. We're going to take a journey that scales all the way from microscopic molecular reactions right up to massive, high-speed mechanical engineering. It's this incredible world where foundational chemistry is essentially transformed into industrial manufacturing magic. And it's so crucial to understand because these hidden processes literally build the modern world around us, creating everything from the clean water we drink to the materials that make up our homes. So, here's our roadmap for today's tour. 1. Process reactions. 2. Compressor mechanics. 3. Solubility principles. And 4. Separation and purification. Let's dive in.
Section 1. Process reactions, the chemistry of the plant.
Let's look at two absolutely vital inorganic process reactions driving our factory. First up is ionization. This is a chemical change where neutral molecules separate into electrically charged particles called ions, specifically positively charged cations and negatively charged anions. In an actual plant, this principle is the driving force behind ion exchangers, which purify water by swapping out problematic ions for harmless ones. Then we have neutralization. This happens when an acid reacts with an alkali or base to form salt and water. This is an absolutely critical step for safely treating industrial wastewater. By neutralizing harmful byproducts before they're discharged, the plant is actively protecting local rivers, lakes, and the surrounding ecosystems. And the ultimate goal of that whole neutralization process all comes down to this number, 7. On the pH scale, which measures from 0 to 14, 7 represents pure, perfectly neutral water. It's the exact point where hydrogen ions from the acid and hydroxyl ions from the alkali are completely balanced, making the solution totally safe for the environment. All right, let's shift gears to the other major branch of chemistry happening in our factory, organic chemistry. The entire foundation of this branch rests on carbon's totally unique bonding properties. You can actually think of a carbon atom like the ultimate universal Lego block. It has 4 specific vacancies in its outer electron shell. This means it's perfectly designed to snap together and share electrons, forming up to 4 covalent bonds with other atoms. Just like you can build an endless variety of shapes with a versatile Lego piece, this incredible atomic property allows chemical plants to synthesize a nearly infinite variety of complex hydrocarbons. Which brings us perfectly to one of the most important organic reactions in the modern world, polymerization. This is how single molecules, called monomers, link together into massive, long-chain molecules or polymers. It happens in this highly sequential, really fascinating process. Step 1 is initiation. Imagine this as striking a match. A catalyst and heat produce highly reactive free radicals. Step 2 is propagation. This is where those radicals react with the monomers, breaking their double bonds and growing the chain. Picture a massive runaway conga line, pulling in new molecules faster and faster. Step 3 is termination. This is hitting the brakes. 2 free radicals couple together, abruptly stopping the chain's growth. Finally, there's an optional step called chain transfer. This is basically used to stop one chain and instantly start another, letting engineers control the exact weight and properties of the final polymer. This invisible chain reaction is literally what gives us everything from everyday plastics to synthetic rubber. Moving right along to Section 2, compressor mechanics, the lungs of the plant. Now, compressors generally come in a few different forms, but let's compare 2 of the absolute heavy hitters. First, the centrifugal compressor. This machine draws gas into the center of a rapidly spinning impeller. The massive vanes on the impeller literally grab the gas and fling it outward using sheer centrifugal force. This drastically increases the gas's velocity, which is then slowed down inside a widening casing, converting all that speed into incredibly high pressure. Axial compressors, on the other hand, push gas axially, straight along a central shaft. They use alternating rows of spinning rotor blades and stationary stator blades to continuously accelerate and squeeze the gas. They act very much like a giant roaring high-speed jet engine fan, generating massive hurricane-like winds. Basically, centrifugal units are deployed for incredibly high pressures, while axial units are totally unmatched when you need to handle massive flow rates. But here is the dramatic reality of these massive machines. Without a whole host of unsung heroes, these critical auxiliary systems, these high-speed compressors would become millions of dollars of flying shrapnel in a matter of seconds. I'm totally serious. Lubrication systems constantly pump clean, cooled oil to fight extreme melting friction. Seals prevent dangerous, highly pressurized, and often toxic gas leaks. Bearings, including shaft and thrust bearings, take on immense physical loads to keep the rapidly spinning components perfectly locked in position so the blades don't violently smash into the outer casing. Aftercoolers pull the intense, dangerous heat out of the newly compressed gas, and relief valves stand guard 24/7 to prevent catastrophic overpressurization. And all this constant vigilance is absolutely necessary to prevent a terrifying mechanical phenomenon known as surge. If the gas flow dropping through a compressor falls below a minimum stable rate, the gas suddenly becomes unstable. It violently reverses flow back and forth inside the compressor casing. This causes severe vibration, massive pressure fluctuations, and a horrifying banging sound that can literally tear the machine right off its foundation. To combat this, automated control systems have to instantly open a recirculation valve, venting gas back through the compressor to keep the flow rate safely above that critical surge point.
All right, Section 3, Solubility Principles, Mixing and Unmixing.
To really understand solubility, we have to recognize the visual and physical difference between mixtures. On one hand, we have homogeneous mixtures, also known as solutions. Visually, they look like one single substance. Think of a dark red dye perfectly dissolved in water. The molecules are uniformly dispersed, and you absolutely cannot separate them mechanically with a simple filter. On the other hand, heterogeneous mixtures have distinct, visibly separate parts that completely refuse to dissolve into one another. Think of sand mixed with water. No matter how much you stir it, the sand is always going to remain separate and eventually just settle right to the bottom. So when a chemical plant needs to force a solid to dissolve into a liquid to rapidly create a homogeneous solution, operators manipulate 4 physical variables on a massive industrial scale. You can actually think of this just like making a perfect cup of hot tea. First, they apply intense agitation, stirring it rapidly to increase molecular contact. Second, they reduce the particle size of the solid so there's more surface area exposed, just like using fine granulated sugar instead of tossing in a giant sugar cube. Third, they crank up the system pressure, which is especially vital when they're dissolving gases into liquids. And fourth, they increase the temperature, using boiling water to drastically speed up those molecular interactions. But this raises a pretty monumental question. Once we've successfully mixed all these massive volumes of liquids, gases, and solids, how exactly do we isolate the valuable product back out from all the waste? Which brings us to Section 4, Separation and Purification, the final polish. One genuinely incredible method for isolation is crystallization. It essentially pulls perfectly pure solid crystals right out of a liquid mixture. It's highly industrial, sure, but it's actually the exact same scientific principle you'd use to make rock candy. It happens in 2 steps. First is nucleation, which is the creation of small crystal seeds, often done by deliberately adding starter crystals to a solution. The second step is growth. By carefully cooling a hot, supersaturated solution, or by boiling off the solvent through evaporation, the dissolved solid is forced to deposit onto those seeds. They literally grow into pure, geometric crystals that can then be easily filtered right out of the leftover liquid. Let's run through 3 more distinct separation techniques that solve entirely different manufacturing problems. First up is leaching. This removes a highly soluble component from a solid using a liquid solvent. It's exactly the same principle as brewing a hot cup of coffee, where the water leaches the flavor straight out of the beans. Next is liquid extraction. If 2 liquids have boiling points that are just too close for normal distillation, engineers use immiscible solvents. These are liquids like oil and water that naturally refuse to mix. The desired chemical essentially hops from the carrier solvent right over into the extracting solvent. Finally, there's absorption, where toxic or valuable components of a waste gas are removed by bringing the gas into intense physical contact with a liquid, literally scrubbing the gas clean before it ever reaches the atmosphere. Now, we need to carefully distinguish that last one, absorption, from our next concept, adsorption. Notice the D there. To make this unforgettable, think of absorption, with a B, like a sponge soaking up water into its entire volume. Adsorption, on the other hand, is much more like Velcro. It's a process where molecules of a liquid or a gas physically cling only to the outside surface of a highly porous solid. The molecules aren't absorbed into the solid mass at all. They're just trapped on the surface in a microscopic maze. Because of this Velcro-like effect, activated carbon is the ultimate industrial adsorbent. To put that into perspective, a single handful of activated carbon has the same surface area as an entire football field. That's insane, right? By treating materials like coal with extreme steam, engineers create this unimaginably extensive microscopic maze of pores. This massive, sprawling surface area is perfectly designed to trap organic pollutants, making it incredibly effective for purifying industrial wastewater and scrubbing toxic air. So, we've seen how simple atoms are bonded like building blocks, how massive machines breathe and roar to keep the plant alive, and how physical properties are cleverly manipulated to separate the pure from the impure. It's an invisible symphony of science and engineering operating 24 hours a day to build our world. Which leaves us with this final thought. If a single chemical plant harnesses this much intricate science every second of every day right now, what entirely untapped processes and reactions will drive the factories of tomorrow? Thanks for taking this conceptual tour with me. Keep exploring and keep learning.